So we have finally arrived at the very important property, the least upper bound property, or the property of the supremum, that this newly defined set R has, that Q didn't have, the rational numbers didn't have before. And in order to show that this holds for this new um, set R, we need to, I mean, restate everything about upper bounds and least upper bounds we defined previously, and state it in terms of cuts, so to remind everyone what we are really after. So what we have so far, so remember, what modulo some exercises that you need to complete. What do we have? It's good to go over these things. To make sure that we keep track of everything that we've done and what remains to be done. What we have so far. So we have shown that R is an ordered field, and this means several things. We define plus, define the product, and we've shown, or you've shown, that all the known properties for plus and times that Q enjoys also hold for R and these new notions of addition and multiplication. So we know that our definitions of addition and multiplication to satisfy all the properties that we know, like commutativity, associativity, and the existence of inverse. There's an identity element in all that, and we managed to accomplish all of that by remaining inside R's in the set of Dedekind cuts, which is what we wanted. Now we can also show that the properties they're related to, such as distributed property, also holds in this case, and the properties for cancellation as well. So this is an exercise again for you. I mean, you remember that you have some homework to do, but if x plus y is less than or equal to x plus z, let's use the notation of sets. So A plus B is less than A plus C. Then this implies that B is less than or equal to C. So if this is a very important property that the rationals have. This is a property of an ordered field. And to see this, remember this is just a notation for a set. And this is a set. This is the set of all the rational numbers that can be written as the sum of an element in A and an element in B. And the same thing for an element in A and an element in C. So the set of numbers that can be written this way, picking one element from A, picking one element from C, and adding them together. And that and this basically means that you can cancel out the A. So on both sides. This is actually not immediate. You may think that this is trivial, but the point here is that, this is just going to be a quick sketch, so to give you an idea, this is not trivial. So if you have an element A in A, and B in B, you know that A plus B is in A plus B, and you know that that's containing A plus C, so that means that A plus B is also in A plus C. But this doesn't mean that A plus B, at least not right away, A plus B is equal to some A plus some other number here that you will be able to cancel out to get the B's that then will allow you to say that one is containing the other. There are many ways of writing the same sum. So this may be equal to some other number R plus S, where R is in A and S is in C. And you have to show from this that if this is the case for every element in A and any element in B, then you can conclude then that B is contained in C. So in particular, you should be able to deduce that this element here, B, should be in C, should be an element of C as well. Okay, so how do you do that? So as you see, it's not a trivial statement, but we do have all these properties available for us for this set R defined in this way, which is kind of cool given that everything worked out in a more or less natural way. We had some complications along the way when defining the additive inverse. It was not just a simple thing to do, and this is the first thing that would pop to our heads would not work, and then when we defined the product, we had to define it using some steps, considering first only non-negative cuts. So there are many things that I'm just leaving for you as an exercise. Most of them, I'm commenting on some things you need to pay attention to, but most of the proofs are come from chasing definitions and being very careful using the properties of Dedekind cuts. Most importantly, the most important one that you actually use most of the time in the proofs is the fact that one can and yeah, the C2, which is the property that tells you that if you have one element in a cut, then all these smaller elements are in there as well. Okay, so if you're just careful about all of these things, then all the other all the other statements that we've left as an exercise should follow. At least, if not easily, well, without major problems. But as I said, as I tried to point out with this example here, they're not all that immediate. In fact, some care had to be put into constructing the real numbers. But as I said, so this is what we have so far. So we have the R constructed in this way, it's an ordered field. We have all the properties and everything we want. But now we need to worry about the topological property of, for those of you who know a little bit of analysis, the least upper bound property, or the supremum, is what makes R as a set of real numbers complete. Well, you don't need to know what that is, but yeah, but I'm just giving you something. Just relating this to something you may have heard of before. So, least upper bound property for R. Least upper bound property for R. So now we have we have constructed the real numbers, and we managed to keep all the algebraic properties. Now we turn to the notion of upper bound. Well, this is basically, this is already defined. Once you have an order, there's only one way of defining this, and you have an order set. But in the book, they decided to go over this definition again. This is the definition we saw in a previous module. But now this is adapted. It's basically just a reminder. Definition 8.6.6. So that we have a set, and we use calligraphic A, which is a subset of R. R is a set of Dedekind cuts, so we're not going to allow ourselves to call it the real numbers just yet. Is said to be bounded above if there is a B in R such that A is less than or equal to B for every element in this calligraphic A, for every A in A. Going back to the set notation, all of these Dedekind cuts, if they're, you have a family of Dedekind cuts, a collection of them, and if there is a Dedekind cut that contains all of them, then you say that that collection of Dedekind cuts is bounded. It's a natural thing to say, to consider. Now, let's turn to the least portion of this least upper bound discussion. So what is least upper bound? The least upper bound for a set, again, calligraphic A, subset of Dedekind cuts, is cut S such that two things hold. S has to be an upper bound. First of all, it's going to be the least upper bound. It has to be an upper bound. For calligraphic A. And also, if you have any other upper bound, then that must be greater than or equal to S. So if B is any upper bound for calligraphic A, then S is less than or equal to B. So if you have any other set that contains all the Dedekind cuts in A, then that contains this upper bound S as well. Okay, so now we know. So we know what means to be bounded, and for a family or a collection of real numbers to be bounded. We know potential real numbers, the Dedekind cuts to be bounded, and we also know what is a least upper bound. So what's next? What's next is the least upper bound. I mean, proving that, in fact, any bounded collection has a least upper bound. This is part of exercise 8.6.8 stated here. So if you have a collection of Dedekind cuts, it is a non-empty collection, that is, and that is bounded from above then A has least upper bound. In fact, that least upper bound is the union of all the elements in A. We denote this least upper bound by S, because S stands for supremum, and this is what we're trying to show it exists. So this is something that we'll need to show, and we'll do that in the next video. This is getting a little bit longer than expected. So we need to show a bunch of things. First of all, that S is going to be a cut, otherwise we haven't accomplished anything. We want to have a supremum within the same set of numbers that we were considering. if we have to, of course, I mean, the set of rational numbers that are smaller than square root 2 has an a least upper bound, has a least upper bound in R, which is the square root of 2, right? But if you consider just sitting inside Q, that would mean the upper bound for all the least upper bound for all the numbers such that their squares are less than 2, then that would not have least upper bound inside Q, inside the set of rational numbers. So if you have to go outside of the rational numbers, then you're in the same spot as before. So if we had defined the real numbers, and in order to have a least upper bound, you have to go outside of the rational numbers, you wouldn't have accomplished much. So every set of this Dedekind cuts that is bounded has a least upper bound inside the set of Dedekind cuts. And this is the least upper bound property of the real numbers. I mean, it will translate into that. And this is what S will be. I mean, the union of all the elements in the collection. And that's what we'll do in the next video. Okay, and we need to show that, okay, first of all, it is a cut. We need to show that it's an upper bound, and finally an upper bound for the collection, and finally we need to show that if you have any other upper bound, then that upper bound is greater than or equal to S. Okay, and that's what we will do.